Pearson correlation is used to assess the strength and direction of the linear relationship between two continuous variables. It answers the question, as one continuous variable increases or decreases, does the other tend to do the same, and how strongly? Example is could be a relationship between cholesterol and systolic blood pressure. Pearson correlation, which is denoted by small r, the values they range between -1, which is a perfect negative relationship, and 1, positive 1, which is a perfect positive relationship. For example, if with each unit increase in weights, there is a perfect 1 unit decrease in diastolic blood pressure, you will see a graph something like this, which will be very close to -1. And if with each unit increase in the exposure of our interest leads to exact 1 unit increase in our outcome, we will have a perfect positive relationship. For example, maybe with each unit increase in cholesterol level, there is a 1 unit increase in systolic blood pressure. So in that case, there will be a perfect positive linear relationship. And if the R value is close to 0, it means that the increase or decrease in the exposure of our interest is not affecting the value of our outcome. So the values of the Pearson correlation are between -1 and 1. They are closer to the either extreme if there is a high degree of linear association between the two variables. The values will be close to 0 if there is no linear association between the two variables. They will be greater than 0 if there is a positive or upward slope linear association, and if they are less than 0 if there is a negative correlation. For example, in this table we see that if the R values are between, say, 0 and positive 0.19, this is a very weak positive correlation, or almost close to no correlation. 0.2 to 0.39 will be again weak correlation. Somewhere close to 0.4 and 0.6, we will call it a moderate correlation. 0.6 to 0.8 is a strong correlation, and 0.8 to 1 will be very strong correlation. And same is applicable when it comes to the negative values. You use Pearson correlation when both of your variables are continuous, both your exposure of interest and your outcome of interest are continuous. The relationship between the two variables need to be linear. As we will see in the next slide, curvilinear relationship cannot be measured through Pearson correlation. The data needs to be normally or roughly normally distributed. And there shouldn't be any major outliers, as we'll see in the next few slides. We can have multiple kind of a scenario when it comes to the relationship between two continuous variables, exposure and outcome. As you see on the top left, there is a linear relationship. As the exposure of interest is increasing, the outcome of interest is increasing, and we see almost positive 1 kind of a relationship between the two. This is the ideal situation for Pearson correlation. There can be other situations. For example, the one on the top right, we see that it's kind of a quadratic relationship. There are certain hormones, there are certain chemicals in the body which are lower in the start of the day, at the end of the day. They might peak somewhere in the middle of the day. In such kind of a relationship, Pearson correlation should not be used, and it might give us misleading kind of results. Then on the bottom left, we see that there is cyclical kind of relationship, maybe seasonal. some of the values which are related to, say, summer, spring, fall, or winter kind of factors might be affecting these variables. Again, in such kind of relationship, Pearson will give us the wrong results or misleading results. And finally, on the bottom right, we see that there is almost no apparent relationship between the two variables. Again, we shouldn't be using Pearson correlation in such kind of situation. There are some critical notes when we are running a Pearson correlation. Number one is that the R measures the linear relationships only, as we have seen in the last few slides. And a correlation near zero doesn't rule out a non-linear relation, as we saw in the previous slide. There can be cyclical or quadratic kind of a relationship, but Pearson correlation would not be able to find out or measure that kind of a relationship. Outliers can greatly affect or distort Pearson correlation R. And finally, as we have discussed it many times, correlation does not imply causation. There could be confounding variables that may distort the relationship between our outcome of interest and our exposure of interest. For the hypothesis testing for Pearson correlation, our null hypothesis would be, now here you see the symbol rho for Pearson correlation, which is in fact the symbol for the Pearson correlation for the whole population, as was the case, for example, in case of mean that we use normally mu for the population and simple x for the sample. Same is the case here. We use R for the sample and rho symbol for the population. So the null hypothesis would be that rho, that is the population correlation, is zero, meaning that there is no correlation between the exposure and outcome. An alternative hypothesis will be that the rho is not equal to zero, meaning that there is no correlation between there is a correlation between exposure and outcome. But please note that a small p-value means that correlation is statistically significant. But in case of correlation and Pearson correlation, it is very important to note that the effect size, the true value of R, is more important than the p-value alone, especially when it comes to the large samples. So again, Pearson correlation is highly susceptible to outliers, especially the extreme ones. A few or even a single extreme data point can either inflate or deflate R. For example, you can see it in the figure on the right that there is a R value of 0.96 here. The line is almost passing through all the data points. But if there are few outliers, as you see in the bottom figure on the right, we see that there are like 4 outliers here, which are pulling the whole line down, and it has brought whole correlation to at least by 20 points down, or 17 or 18 points down. See, from 0.96 to almost 0.71. So these can mask the true relationship between the two continuous variables. The best practice is that we visualize with a scatter plot before we run Pearson correlation and see if there are any points which are valid. And when it comes to results, we normally report the correlation values with and without the outliers.